In this example, we're going to look at linearizing experimental data. Now, as you can see, we've got an question. The data below follows the relationship y equals ax to the power of b for some constants a and b. So you've done an experiment, you've taken down some data, and this is the table. When x is 2, y is 8.5, and so on. And you're told that this data should have a y equals ax to the b relationship. Then appropriately linearize the data to find the values of a and b. So we could just plot that data as it is, and would end up with some curve. I don't know exactly what it would look like, but roughly a curve looking like this sort of shape. And unfortunately, it's not very easy to work out the values of a and b from the shape of that curve. What we much prefer to do is to turn the data into a straight line graph, that is, linearize the data. And if we have a straight line graph, we can work out the gradient and intercept of a straight line graph quite easily, and we can use that to work out a and b. So we'll see how to do that. So how do we linearize this data? Well, often when we have to linearize something like this, we're going to look at our formula y equals ax to the b. And what we're going to do is we're going to take logs of both sides. So it doesn't matter what type of logs, I'm going to take natural logs. So natural log y equals natural log of ax to the power of b. And now we can use some log rules that we should be familiar with. Log of ax to the b, log of two things multiplied together is the same as log of a plus log of x to the b. And we also know that log of x to the b, the power rule of logs, is just the same as b times the log of x. So this thing turns into log of a plus b times the log of x. So log of y equals, just to write that down as one line, log of y equals log of a plus b log of x. Now actually this sort of form of equation is much more akin to a straight line sort of form. Compare that with y equals mx plus c. It's the same sort of idea. Rather than y, we now have log of y. Rather than mx, we actually have b times log x, and instead of c, we have log of a. So if we plot log y against log x, have a look at this form, log y is log a plus b log x. So the gradient is the thing in front of the log x, that's the b. So the gradient is b, and y-intercept is the value of c. Well, that's just corresponds with log a, which sort of just matching up form. Now, obviously, this only works if this relationship really is y equals ax to the power of b. But if the relationship really is log equals y equals ax to the power of b, if we plot log y against log x, we should get a straight line. So that's what we're going to do. We're going to, first of all, we're going to take our table and take this data here, and rather than x against y, we need to plot log x and log y. So we need to work out those values first of all. So I've calculated those already. So log x and log y. So when x is 2, log x is 0.69. When x is 3, log x is 1.10. When x is 4, log x is 1.39. When x is 5, log x is 1.61. So all I've done is taken these values of x at the top and worked out the log of each of those values. We're going to do the same for the y's. So when y is 8.5, log y is 2.14. When y is 23.3, log y is 3.15. When y is 47.5, log y is 3.86. And finally, when y is 84.7, log y is 4.44. Okay, so that is our new sort of linearized data. So hopefully, if we plot this this new data, we should get a straight line. So let's. I'm not going to do it properly. Obviously, if you're doing an exam or something, you would plot this data quite accurately. But let's just check we do get something that looks like a straight line. So I can't draw this very easily on a computer. We're going to plot log y on the y-axis and log x on the x-axis. So when x is 0.69, then log y is 2.14. So let's have 0.69. Let's just see how roughly we can do this. Let's say that's 1, that's 2, that's 3, and then on the y-axis, we can say that's 1, that's 2, that's 3, that's 4. Okay, we're going to plot something like that. Okay, so 0.69 is about here, and 2.14 is about here. So that's our first point. 1.10 is about here, and 3.15 is about here. 1.39 is about here, 3.86 is about here, and 1.61 and 4.44 is about here. Okay, now you can see these do indeed look roughly like a straight line. Obviously, as I said, it's quite hard for me to do on the computer, but if you did this accurately, you should have a pretty good straight line. And if you drew the sort of best fit line through these points, then, again, I can't do this very well on a computer, you end up with a line like this. Obviously, that should go through all those points, really, especially if the experimental data is any good. And then if you look at this, you see the intercept here is about, it turns out to be about 0.4. About 0.4 here. And remember, the y-intercept is log A. So we get log A is approximately 0.4. And if you take exponential to both sides, that means A equals e to the 0.4. And I think you get, that's about 1.5. Okay, obviously there's a bit of rounding here where I've not drawn things perfectly accurately, but that's the idea. So A is about 1.5. Similarly, if you take the gradient of this graph, you could take any 2 points on the best fit line and take the difference in y divided by the difference in x. And remember, the gradient we worked out should be equal to b. So b equals, let's say, change in y over change in x. If we take 2 points on the line, work out this change in y over change in x, I think you get about 2.5 is the gradient of that straight line. So you could measure it on the graph. You don't even have to draw the graph. You could just take the table of results and use that to work out the gradient of this straight line. Just take two y values and divide the difference and divide by the change in x values. And then we've worked out what a and b are. So our relationship is y equals ax to the b, I think it's going to be 1.5 x to the 2.5. And we've linearized our data to work out the values of a and b.